Good morning and welcome to today's electronic design webcast. Our topic today, automotive 48-volt systems are here, enabled by Semiconductor Solutions, sponsored by ON Semiconductor. I'm David Maliniak with Endeavor's Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. This webinar technology allows you to resize the presentation by clicking the maximize icon or by dragging the lower right corner to enlarge the window. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Jay Nagel is a Senior Product Marketing Engineer for the Automotive Market Segment at ON Semiconductor, located in Phoenix, Arizona. Jay has over 14 years of experience in the automotive and semiconductor industries. He is responsible for helping customers develop reliable, cost-competitive system designs using components from ON Semiconductor's broad automotive portfolio. You can learn more about our speaker by clicking on the blue speaker bio widget on your console toolbar. Now let me turn things over to our presenter. Jay, the floor is yours.
Thank you very much, David. So here's today's agenda. We are going to start with an overview of ON Semiconductor, followed by our leadership in automotive semiconductors, some background on the electric vehicle market, an overview of 48-volt systems topology, some education on how regenerative braking and three-phase inverters work, and what competitive solutions ON Semiconductor provides in its automotive portfolio for this vehicle segment. So before we get into the main topic, I want to give you a short introduction to ON Semiconductor, which is an American company based in Phoenix, Arizona. The company was spun out of Motorola in 1999 and went public in 2000. Over the years, ON Semi has grown organically and has diversified our product and technology portfolio through multiple acquisitions, including Cherry Semiconductor, Aptina Imaging, Fairchild, and most recently, Quantenna. With over 34,000 employees worldwide and $5.5 billion in sales, ON Semi offers a wide range of products from imagers to power modules to mixed signal and analog devices that meet the needs of industrial, consumer, IoT, and automotive markets. Our highest revenues worldwide originate from the automotive and industrial market segments, so we're really strong in those areas. This slide shows the breadth of ON Semi's global design, manufacturing, and sales locations. Many of these locations are a result of acquisitions, leaving areas of expertise intact, but also because we want to be close to our customers to ensure the optimal level of support. A key differentiating factor for ON Semi is that our manufacturing is vertically integrated. We have the ability to produce silicon substrates at our front-end facilities and one of the world's largest and most efficient back-end final assembly operations. In 2019, ON Semi shipped over 66 billion parts. Automotive is one of ON Semi's largest markets and a focus of strategic growth. As you can see, global semiconductor sales are expected to grow from $36 billion in 2020 to around $68 billion in 2025. While we offer products used in all electronic subsystems within the vehicle electrification and vehicle automation are where we see the greatest growth potential for the market at ON Semi. If we first look at vehicle automation, ON Semi is the market leader in image sensing for advanced driver's assistance systems and automated driving. With recent LiDAR and radar technology acquisitions and advancements in power supplies designed for automotive sensors, ON Semi can offer a full suite of sensors needed to automate tomorrow's vehicles. Likewise, we can see that there will be a 10x increase in semiconductor content over today's internal combustion engines. onsemi's portfolio of IGBT and wide bandgap discretes and power modules are well positioned to capture a significant share of this market. So now let's take a look at how onsemi's technology enables one approach to vehicle electrification, the 48-volt mild hybrid system. But before we get into that, let's take a look at the emerging electric vehicle market, its enablers, challenges, and benefits. Electric vehicle solutions encompass four main approaches: mild hybrid EVs, which we're going to focus on today, full hybrid EVs, plug-in hybrid EVs, and full electric vehicles, battery electric vehicles. This chart shows the forecasted growth over the next few years. Overall, electrification will grow by a CAGR of 24% between now and 2024, with mild hybrids and battery electric vehicles accounting for the largest growth segments. Likewise, traditional ICE vehicle volumes will decline globally by -3% during the same period. There are many factors driving the shift, including legislation designed to reduce greenhouse gas emissions and technological advancements that are enabling a cost-effective transition to electric vehicles. The US, European Union, and Asia have put in place strict targets to reduce CO2 emissions from automobiles, in many cases targeting reductions of up to 50% by 2025. The demand for more fuel-efficient, cleaner transportation can be met by innovation in the semiconductor industry to develop smaller, higher efficiency, less costly power modules that are used to electrify the global car fleet. onsemi is a leader in this area, and we're going to share some of those innovations with you. Electrification, though, does have its challenges. Batteries, which make up a bulk of the cost of an EV powertrain, still remain expensive, but innovation is quickly driving this cost down too. Also, what to do with the batteries at the end of the vehicle life remains an open topic. Do the materials get recycled? Is there a large enough secondary market for battery use? And so on. Battery electric vehicles have a limited range, although it's improving, but how fast can batteries be recharged while on the road compared to the time to fill a gas tank? Are there enough fast charge stations available in the places people need to charge their vehicles? Electric motors in particular use magnets that contain rare earth materials that are only available in limited locations. Efforts are currently underway to find alternate materials and technologies to mitigate the risks associated with rare earth materials, such as using induction-type motors. Broader availability of electric vehicles brings a range of benefits, including instantaneous torque, doing that 0 to 60 in 3 seconds, a corresponding reduction in noise pollution, and the total cost of ownership goes down. More importantly, reductions in carbon dioxide emissions, cleaner air, and a positive impact on climate change. So now let's start with our first polling question. Which of the following are goals for vehicle electrification? CO2 emissions reduction, lower cost of ownership, instantaneous torque, or all of the above? So let's take a second to answer that question, and then we'll go over the answer. Wow, everybody is awake this morning and paying attention. All of the above. 100% of you answered that question correctly. So before we discuss mild hybrid architectures in more detail, let's review the electric vehicle types available on the market today, their differences, and contributions to creating that greener footprint. A microhybrid utilizes the standard internal combustion engine. Instead of using a standard alternator inherent in an internal combustion engine vehicle, it uses a belt-driven starter generator that is powered from the 12-volt battery. This modification enables the engine to stop running when the vehicle is not moving and the driver has their foot on the brake pedal. As soon as that pedal is released, the engine will restart. This eliminates engine idling, and that translates into about a 3 to 4% decrease in CO2 emissions. Now, the mild hybrid vehicle and the hybrid electric vehicle. So these vehicles are an evolution from the micro hybrid. The mild hybrid has an electric motor that supplements the internal combustion engine to implement the start-stop feature, regenerative braking, vehicle coasting, and depending on the topology, propulsion at low speed conditions that contributes to a decrease in CO2 emissions by around 4 to 10%. In addition, these vehicles contain both the traditional 12-volt lead-acid battery and a 48-volt lithium-ion battery. The electric vehicle, or the hybrid electric vehicle, contains a larger battery ranging between 250 and 360 volts that supplements a smaller, optimized internal combustion engine capable of operating at full electric mode for a short time span with assistance from the motor. This translates into a CO2 emissions reduction target of between 25 and 30%. Now moving to plug-in electric vehicles, compared to the full hybrid vehicles, the plug-in hybrid has a much larger battery size which enables operation for a longer distance range in full electric mode without assistance from the engine, but not completely. You still need the internal combustion engine. The battery will be recharged via regenerative braking and also through the power grid. The longer range capability in a full electric mode will contribute to a CO2 reduction between 50 and 100%, but not all the way to 100%. That's where the battery electric vehicle comes in. The battery electric vehicle utilizes an electric motor 100% for vehicle propulsion with zero emissions and close to 100% CO2 reduction for the entire range allotted by the battery charge. So overall, the trade-off between all vehicle types is CO2 emissions reduction coming with higher vehicle costs. The mild hybrid vehicle will be a popular choice because it creates the sweet spot for the consumer to achieve CO2 emissions and decrease fuel consumption at a very reasonable cost to the consumer. For example, compared to full hybrids, mild hybrids offer 50% of the CO2 reduction for approximately 30% of the cost of a full hybrid system. So on to our next poll question. All start-stop systems are 48-volt mild hybrid systems. Is that true or is that false? Give a chance for the audience to respond. 100% of you said that answer was false, and that's correct. So when taking a deeper dive into the 48-volt architecture, I will discuss the system-level blocks of the 48-volt mild hybrid systems, how these components are integrated into the drivetrain, and the component solutions that ON Semiconductor offers to enable optimal performance in the vehicle. 48-volt systems will contain two voltage subsystems powered by a 12-volt lead-acid battery and a 48-volt lithium-ion battery. The typical drivetrain will contain the 12-volt starter and internal combustion engine, a starter generator motor will start up the engine, provide a boost in the torque force for acceleration, and charge the battery during regenerative braking. The starter generator motor is either integrated into the transmission or connected to the internal combustion engine using a belt. The starter generator motor is powered by the 48-volt battery using a three-phase inverter connected in line with the motor. With both 12-volt and 48-volt powered systems in the vehicle, a bidirectional converter is implemented to be able to transfer energy between both batteries. The 48-volt battery also drives loads that require higher power to operate, such as an electric supercharger, which is a device that forces air into the engine when a burst of power is needed for acceleration. And that's represented by the 48-volt auxiliary pop-out that you see on the screen. So let's take a brief step back to answer the question of why there is a 48-volt and 12-volt in a mild hybrid vehicle, And why 48 volts to begin with? The 12-volt battery functions to power devices that you would find in a traditional internal combustion engine vehicle, such as interior electronics, body control modules, infotainment, and telematics systems. So in order to develop fuel-efficient vehicles with performance features attractive to the consumer, heavy-duty pumps, compressors, turbos, and suspension components are integrated. Now, these components specifically require much more power to operate than what a 12-volt lead-acid battery can provide in terms of power. In addition, the lead-acid battery cannot provide the acceleration boost that a higher voltage can. The 48-volt system is an optimal voltage source to support the drivetrain, since it's a generally safe voltage for humans to operate with, and a higher voltage can allow for a significant reduction in interconnect cabling to run the high-power systems. Less current means that smaller wiring can be used to reduce the size and weight of the vehicle wiring harnesses, which leads to the coveted CO2 emissions. So one of the goals of electrification and creating the systems is to create low-cost, low-weight type of devices that's going to enhance the ability to reduce those CO2 emissions. Mild hybrid vehicle types and their level of capability are distinguished through their architecture. The P0 through P4 configurations represent the positioning of the electric motor with respect to the drivetrain. Depending on the configuration, different levels of functionalities are possible, yielding differences in overall system costs, fuel efficiency, and performance. The PO configuration represents an electric motor connected to the internal combustion engine using a belt in what is termed a BSG, which stands for belt starter generator. In a P1 configuration, the electric motor is connected directly to the crankshaft of the internal combustion engine in what is termed an ISG, which stands for integrated starter generator. The P0 and P1 configurations are the most prevalent topology for mild hybrid vehicles today. In a PO configuration, the integration costs are minimal, but the resulting frictional losses due to the belt connection compromise the efficiency of the system. But in a P1 configuration, you can achieve a bit higher efficiency since you are not connected to a belt, and that eliminates the frictional losses, and you can achieve a higher torque for better boosting. Moving a step up further, in the P2 through P4 configurations, the electric motor is positioned where it is not connected to the drivetrain of the internal combustion engine, but it's integrated with the transmission as an integrated starter generator. These types of configurations yield the highest efficiencies, the best energy recovery and recuperation through regenerative braking, and even very low-speed electric drive coming at an increased cost. That's the trade-off that you have. P2 and P4 configurations are not prevalent today, and they're under development by OEMs. Okay, so it's time for another poll question. Which vehicle functions can be enabled with a 48-volt mild hybrid electric vehicle architecture? Is it A, regenerative braking, B, additional power for a few seconds, C, powering 48-volt auxiliary systems such as electronic power steering and HVAC, or is it D, all of the above? So go ahead and please answer the question. We'll take a few moments here, and then we'll see what everybody says. Most of you got it right. We have a sharp audience today. I'm so happy about that. The answer is all of the above. So depending on the topology that you're using, you can have the ability to have all these functions, but ubiquitous amongst all the topologies are these particular features, with very limited electronic drive occurring in a configuration that's P2 through P4. So very good. Okay, we're going to take a little bit of a step back here. I'm going to talk a little bit about how the three-phase inverter drive works. So this is a topology that's typically done for motor control. It depicts 6 power switches in a three-phase bridge, also known as 6-pack configuration. It shows 6 power switches with MOSFETs. The three-phase inverter is formed using 3 half bridges. These half bridges are constructed with a high-side switch and a low-side switch. The output of each half bridge is connected to one of the 3 phases of the induction motor. The image at the bottom shows how, through pulse width modulation techniques and advanced motor control switching patterns, the high voltage battery is connected across the 3 windings of the induction motor, generating an alternating current through the motor's phases, producing the torque required to propel the vehicle. This AC current can be adjusted for both amplitude and frequency by changing the PWM commutation patterns controlling both motor speed and the torque. So now we'll take a step back and see how regenerative braking works. Regenerative braking is when braking energy from a moving vehicle is transformed into electrical energy. This energy is restored into the high voltage battery. This feature is implemented using the power switches in a boost converter topology. When the vehicle is moving and the induction motor is turning, this creates a back EMF voltage drop that can be modeled as depicted on this slide. Looking just at a single phase, the main controller can close, for instance, switch number 4. What that does is it effectively shorts the motor winding to ground, which breaks the vehicle and charges the motor's series inductance. This energy is then transferred to the high voltage battery by turning off switch 4 and allowing the energy stored to flow through the fast recovery diode of switch 3 back into the battery. Some OEMs actually enable this feature on demand in order to brake the vehicle without actually activating the hydraulic disc brakes. So we'll go to another poll question here. And the question reads as follows. Mild hybrid systems achieve what level of fuel savings? Is it A, between 4 and 10%, B, between 10 and 20%, or C, greater than 20%? Well, I'll give you guys a few moments to select the answer. We'll see what the poll says. Okay, looks like most of you selected A, some of you selected between 10 and 20%, and some of you selected greater than 20%. So just to review again, a mild hybrid vehicle can achieve between 4 and 10%. You get probably between 10 and 20% if you had a full hybrid electric vehicle with a larger battery size. So if you remember earlier in the discussion, we talked about the differences between the electric vehicle topologies and the level of CO2 emissions reduction that you're going to get. So with the 4 to 10%, you really get that from the engine start-stop. You get that from the coasting feature. And you also get that through the regenerative braking. Unfortunately, you don't get a very, very high level of savings compared to the other vehicle types, just because of the fact that you cannot have full propulsion from the battery at a high range or at a high level of speed. So now we're going to talk a little bit about the 48 volt to 12 volt converter. So the 48 volt to 12 volt converter is a multi-phase synchronous buck boost bidirectional voltage converter. It functions as a buck converter to use the energy from the 48 volt battery to charge up the 12 volt battery, and also has a boost converter that uses the energy from the 12 volt battery to charge up the 48 volt battery. A single phase is shown here for simplicity, although you can have multiple interleaved phases depending on the power level that's required. So the main blocks that constitute this converter are the source disconnect switch, the buck boost half bridge, the current sensing stage, and the load disconnect switch. The source disconnects and load disconnect switches permit disconnection of the converter from the 48 and 12 volt battery using low RDS on, high drain current MOSFETs controlled by gate drivers. High and low side gate drivers and 80 to 100 volt MOSFETs create a synchronous buck boost stage intended to minimize the switching and conduction losses and maximize the power efficiency of the system. The high and low side FETs in the buck boost stage control the direction of current flow between the batteries. A current sense amplifier is needed to monitor the inductor discharge current to regulate the battery charge. Since there are very high currents running through these MOSFETs, the MOSFETs need to have low resistances and favorable thermal attributes. ON Semiconductor has a broad automotive portfolio of MOSFETs, amplifiers, and gate drivers in various configurations and packages to construct a system at the target efficiency, which is usually about 95 to 96% for a 48 volt to 12 volt bidirectional converter. If the designer is seeking an integrated solution, ON Semiconductor has an automotive power module that contains an integrated solution for a three-phase bidirectional converter with three half-bridge circuits integrated into one package. So let's talk a little bit about 48 volt belt start generator, integrated starter generator, traction drive systems. So the BSG, or the belt start generator, and the ISG, the integrated starter generator, which we talked about earlier, its traction drive is very similar to the construction of an inverter for a battery electric, full hybrid, or plug-in hybrid vehicle, but it operates at a much lower voltage level due to the fact that you have a 48 volt battery and not a higher voltage battery in the 400 to 800 volt range. For this solution, 80 and 100 volt MOSFETs are used to source the current from the 48 volt battery to apply a three-phase AC current to the electric motor windings. Gate drivers are then used to create the PWM signals to switch the MOSFETs at the required frequency. Current sense amplifiers are available to monitor the current applied to the phase windings of the motors, with a broad portfolio of components for signal processing and conditioning of sensor data, CAN transceivers for in-vehicle communication. We also offer a grade 0 EEPROM for parameter storage, small signal components such as digital transistors and switching diodes to support the operation of the microcontroller, and also ESD protection devices with fast transient clamping capability and low capacitances that protect the integrity of critical signals. And now on to our flagship product for the 48 volt inverter system. It will be our half-bridge 3 to 6 phase automotive power module configured to be able to run either a 3-phase or a 6-phase motor, which is pivotal to meet the redundancy requirements when considering functional safety requirements. Each automotive power module consists of 2 high-side and 2 low-side devices mounted in parallel configuration. The power module is a highly integrated design with low thermal resistance and high current carrying capability, making it a high power density product. The device contains snubber circuits for improved EMI performance and enables lower stray inductance through its interconnect by being able to connect directly to the DC bus bar. One of the key advantages of this product, though, it's transfer molded construction versus being a gel-filled module. That translates into a higher reliability, lower thermal resistance, and a product having less warpage. So we have a very broad automotive portfolio for a complete system solution. So we can provide everything under the sun for a 48-volt system. We can provide the MOSFETs, the APM modules, the current sense amplifiers, the power management, the in-vehicle network transceivers, and some of the supporting components. We talked about the EEPROM, the ESD protection, the small signal discrete, such as BJTs and diodes. What's important overall, and what we're striving to present with our solution, is we're trying to present a solution that's low cost, that's low weight, enables smaller package sizes, enables smaller interconnect, so that companies can build vehicles that maximizes the reductions in emission. So to conclude this presentation, here are some models of our 25 kilowatt ISG reference design that, in addition to the automotive power module, populates AEC-Q 100 and 101 components from our automotive portfolio. This design was in display in our booth at the CES Electronics Show earlier this year. So I don't know, for those of you who were at CES, if you were able to check it out. But what this solution represents is a pictorial of being able to provide the complete solution for the motor drive required to operate the electric induction or permanent magnet motor that is a part of these systems. I want to thank everybody for their attention. And I'll go ahead and turn it over to David for a Q&A session.
All right, Jay, very good. Thank you. Interesting presentation. So a few of you have already submitted questions, and we'll jump into those. If you would like to submit a question now, type it into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form located on the bottom of your screen. All right, the first one that I have for you, Jay, is what vehicles currently are in the market today that have a mild hybrid configuration?
So here in North America at Fiat Chrysler, we have the Ram 1500 pickup. Mercedes and Audi also have mild hybrid vehicle models, and Volkswagen will have vehicles soon.
Okay. Another question is, could you please explain the reason for a 48-volt battery disconnect?
So the 48-volt battery disconnect switches are meant to be safety switches in case that there's any faults coming from any type of overcurrent or transient situation that occurs on the battery. So the switches for the source disconnect and the load disconnect are configured in a back-to-back configuration, one being a reverse battery protection and the other one being a safety switch.
Okay. Next one. What are the design costs associated with electric vehicle development?
So in terms of cost per car, microhybrids have been estimated to be about $100 cost per car. With battery electric vehicles going up all the way to about $11,000 per car. So right now, the battery electric vehicle provides a very expensive proposition, and so battery electric vehicles can take off more in the market if we're able to find a way to reduce battery costs, as was discussed at the beginning of the presentation.
All right. What are the disadvantages or disadvantages of multiple phase bidirectional 48 volt to 12 volt power transfer?
So one of the disadvantages of the 48 to 12 volt bidirectional converter approach, in my opinion, is the fact that a lot of these systems require isolation between the 48 volt battery and the 12 volt battery. So electric vehicles in general require isolation between the very, very high voltage battery, the 400 to 800 volt battery, versus the 12 volt lead acid battery, because you can't really share the grounds, safely between those two batteries. But a lot of OEMs that we see out there, and a lot of our tier one customers still want to implement, some level of isolation between the 48 volt battery and the 12 volt battery, which you don't get, in a 48 to 12 volt converter, in a bidirectional converter. But with that being said, companies are using auxiliary power supplies and flyback converters to be able to create that isolation, and we provide the solutions for those applications as well.
All right. Can you share more about the 6-phase motor control that you mentioned versus standard 3-phase motor control? Okay.
So I did mention functional safety requirements. So imagine a scenario in which you have just a regular 3-phase motor, but there's faults in that motor that cause the motor to not be able to operate properly. There is an auxiliary motor that runs in that case, that's able to bring the vehicle into a safe state, especially if you're operating that vehicle autonomously. So it's basically a backup safety motor, is what we're seeing out there in the market.
Okay. You'd mentioned that 48 volts was chosen over 12 volt batteries because of the higher current requirements of BSG and other new devices. Why 48 volts? Why didn't they go with 96 volts or some other level?
48 volts represents a good threshold for being a safe operating voltage. So higher voltage systems all the way to 60 volts are also going to be in the market, but it's a matter of the highest threshold that you can go to without being able to compromise safety. To a human or to a technician or to anybody interacting with the vehicle.
Okay. What's the highest power of your converter? And he's asking about a cost perspective, and how about trucks or commercial vehicles?
So in a typical, it's depending on the configuration that you're running. The highest power rating of the converter is going to be anywhere between 10 kilowatts and 30 kilowatts.
Okay, and is this applicable to trucks or commercial vehicles?
Yes, it's applicable to trucks. And so one good example that I had mentioned before was the Ram 1500 pickup with its e-torque. That's something that you could very easily Google on the internet to get more information on how that topology is integrated into a truck.
Okay. A comment and a question, I guess. Great CO2 reduction in operation. How about comparison of CO2 loading for component manufacturing versus oil pumping and refining, I should say.
I'm sorry. Can you repeat that question, please?
He's asking if you can compare CO2 loading for component manufacturing versus oil pumping and refining. I guess he's asking about I don't know how to phrase it. Talking about CO2, he says great CO2 reduction in operation. And how about comparing CO2 load for component manufacturing versus oil pumping and refining?
Yeah, I guess it's kind of hard for me to answer that question because I can only talk about CO2 reduction as it pertains to vehicle emissions in this particular case. And so with the different electric vehicle types that we have out there, you're going to range anywhere from between 3 to 4% all the way to 100% with the full electric vehicle.
Okay. On the 48-volt architecture slide, you show a 12-volt starter. Why not make that a 48-volt starter and generator and eliminate the belted machine entirely?
So in the integrated starter generator configuration, you're actually placing the motor in line with the transmission. So you're eliminating the belt that way. You could use a 48-volt motor definitely for the starter. They usually call that a turbo, to give the acceleration boost that you're looking for. But the reason for really going to the belt starter generator configuration is because it's an easy upgrade to the existing internal combustion engine. There isn't much in terms of integration costs and redesign because you're actually adding to the existing internal combustion engine setup that's there right now, using the belt starter generator type of configuration.
All right. Well, what are the kilowatt-hour ratings for 48-volt battery and the peak assist kilowatts for the Ram 1500?
It totally varies amongst suppliers. There's different suppliers in the market where you can find that information. So Continental is an example of one for a 48-volt system that you can get some really good information from their website, pertaining to that. But there's really no average value that I can give you off the top of my head.
All right. In which regions are mild hybrids expected to have the highest volume?
So currently what we're seeing in the market right now is that Europe is having the most stringent requirements. They're actually targeting between 70 and 75 grams per kilometer by 2025, followed by China that's targeting about 95 grams per kilometer by 2025. So I expect that the highest volume is going to be in the European region by the 2024 date, but they're obviously going to roll out in all regions.
Okay. Well, that kind of exhausts the questions that we've gotten. If anybody else has any further questions, maybe we'll give them a couple of seconds to feed those to us. And any comments or questions that aren't answered, we'll get in touch with you soon to answer those. And that concludes today's presentation. So on behalf of Electronic Design, I'd like to thank ON Semiconductor for sponsoring today's event, and of course all of you for joining. Have a great rest of your day.